Okay, so the class that we had yesterday night, we did integration questions in that class. There were quite a few questions that we did. Again, if you missed that class and if you haven't attempted many integration questions yet, please make sure that you do that, because those were some important questions that we did yesterday. We will today continue with where we left functions yesterday. So we're going to continue with that today. Integration questions that you are missed yesterday, in case you missed, please make sure to go through them. They're there in the notes, they're there in the recording as well. And you should do more practice on that as well. Now, let's begin with functions. All right, so what did we start yesterday? We started with this, we started with function notation, that this is just another way of writing equations like these. If we have y equals 2x plus 5, you could also write it like this instead, f of x equals 2x plus 5, right? Which means it's a function of x. Function of x is defined as 2x plus 5. All right. There was this notation that we talked about, f of 3, for instance, what that means. Then we discussed how to find inverse of a linear function. That's something that you've done in O-levels. So it was just a quick reminder of that, the process that you follow for finding inverse of a function. Then this was the more important part that was new for most of you, and that was domain and range of functions. How to find domain and range of functions. So what's domain of a function? It's basically the set of values of x that a function can take as an input. And range is the set of values of y that a function can give as an output. Okay, so values of x is what domain represents, values of y is what range represents. We looked at some conditions that you need to know about for domain of a function. Generally, the domain of a function will be given in the question, and you will be asked to find range of the function using that domain. But there are some conditions that you need to know about still. For example, if you have a square root function, inside square root, you need to know that you need something that's greater than or equal to 0. All right, and using that in this function, for instance, the value of x is supposed to be greater than or equal to -4. Similarly, if you have a fraction and you have x in the denominator, you cannot have 0 because division by 0 is undefined. Okay, that's what we discussed. Then we talked about how to find range of linear functions. We did some examples in this. We said drawing the graph of the function, sketching the graph of a function helps us understand what the range would look like. In this case, we sketched this graph for this linear function and used that graph to find the range of the function along with the given domain, right? So this was the domain given. We used the domain and the sketch of the graph to figure out what the range would be. Now, in this case, it was important to realize that if domain has something like this, x greater than 5, it does not necessarily mean that the range is also going to have the same sign, right? In this case, domain was x greater than 5 and range was y less than -5. That basically is something that you understand from the graph. You look at the graph and see, okay, what's the maximum value on this graph? What's the minimum value on this graph? And based on that, you write down the range, right? We did this, some examples of this. Then we talked about range of quadratic function. This was the most important part because this is the most commonly asked question in the exam. As far as functions is concerned, you will mostly be dealing with quadratic functions. There are other types of functions as well, but mostly they use quadratic functions in the functions topic. So we need to understand how to find range of quadratic functions. So we looked at this particular function and we looked at how to find the range of this function given different domains. We first of all sketched this graph. It's a U-shaped graph and said the turning point is 327. We found the turning point using minus b over 2a. And then given that the domain was any real value, we said the range should be y greater than or equal to 27. But then if the domain was different, x greater than 1, for instance, x less than 0, 1 between 1 and 7, between -1 and 2. We looked at all of these cases and understood how to find range using the graph of the function, using the sketch of the function, right? So that was very important. It was also important to understand when to put the equal to sign with the range, when to not put the equal to sign. So in this case, for instance, domain was from -1 to 2. The equal to sign was here, and the range, the equal to sign was here. So we also talked about that, right? So all of this discussion we did in the last session. It was slightly confusing when you do it the first time. It's slightly confusing because you have to look at the graph and the turning point and see whether the turning point is inside the domain or outside the domain. So it's important to make sure that you spend some time on this, make sure that you understand each of these examples very, very well. And then after doing all that, we came to this conclusion: whenever we are looking to find range of a function, we are basically going to be looking at two things: endpoints of the domain. So whatever is the domain given, we will be looking at the endpoints of the domain, right? We'll see what happens to the function at the endpoint. For example, in this case, we looked at what happens at -1, what happens at 2. And in addition to that, we will look at what happens at the turning point. These are two important points to consider, two important types of points to consider whenever you're finding range of a function. Okay, so that's what we did in the last session. Now, today we want to move on to the next type of function for which we need to understand how to find range, and that is reciprocal function. Let's start with that. Reciprocal functions. Now, this is another type of function that you would see in the questions and past papers. These are called reciprocal functions. There's another name that we have for this. These are also called rational functions. Now, there's a slight distinction between what a rational function is and what a simple reciprocal function is. But for our purposes, we will treat them the same. Basically, these are functions that have some x term in the denominator. All right. So these are functions that have some expression in terms of x in the denominator, right? That's what these functions are. Let me write that down. These are functions that have x terms in the denominator. Now, for example, you could have something like this: y equals 1 over x. All right, this is one possible reciprocal function, y equals 1 over x. You've seen this in O levels as well, in graphs of functions topic. You sometimes used to draw graphs of functions like these. If you were to draw the graph of this function, it would look something like this. It would be in two parts. Why? Because when x is 0, the function is undefined, right? When x is 0, the function becomes undefined because you have 0 in the denominator. You can't evaluate that. So because of that, at x equals 0, the function is not going to have any value, which means the function is going to exist in two different parts. X could be negative, x could be positive, but it can't be 0. On the right side, the graph looks something like this. On the left side, the graph looks something like this, right? So you've seen such graphs in O levels. They used to exist in two parts like this. So generally, whenever you have x in the denominator, you would have a graph that looks something like this. Okay, you would have x terms in the denominator, and the graph will be broken. Why? Because if x is in the denominator, there is a possibility that you could have 0 in the denominator. And if you have 0 in the denominator, the function would be undefined at that point. Okay? So the graph is broken like this. Now, this is what reciprocal functions are. All right. Now, we want to be able to find range of such functions. Now, in our syllabus, these types of functions will not have any turning point. Now, there may be reciprocal functions that do have turning points, as in such functions may exist. But in our syllabus, in functions, we would not get a function that has any turning points. Okay, so no turning points for functions for reciprocal functions in our syllabus. What that means is, whenever you have a reciprocal function, you can assume that there is going to be no turning point. Okay, so in this case, for instance, there's no turning point, right? There's no point where the graph has a gradient of 0, right? It does not, that point does not exist here, where the gradient is equal to 0, right? There's no turning point. There's nothing like this or like this. And that's going to be the case for every reciprocal function that we have, for which we have to find the range. Okay, so you need to remember this. Now, once you know that, remember the two types of points that we said you need to check to find the range of a function. First type was endpoints of the domain, and the second type was turning points of the function. Now, if there are no turning points, that means we only need to consider the endpoints of the domain. That's all that we've got to consider. So we don't have to consider the turning points because they don't exist. So we are only looking at the endpoints of the domain. Okay, so that's all that we're going to be looking at for reciprocal functions when we have to find range of such functions. Now that we understand all of that, let's take an example of a reciprocal function and see how we can find range of that reciprocal function. So I'm going to write down a couple of examples, a few examples from past papers now, and we will look at how to find range of these functions. First of all, let's say we have something like this. F of x equals 3 over 2x plus 1. We have a function like this, and they have given that x is greater than 0. So we have a function like this. F of x equals 3 over 2x plus 1. The domain of the function that's given in the question is x greater than 0. How do you find the range of this function? That's what the question is. Okay. X is greater than 3. X is greater than 0. That's the domain. What about the corresponding range? Let's see how we're going to think about this. Now, you see, domain is x greater than 0. What does that mean? It could be any value greater than 0, right? Any positive value. So if you were to look at the endpoints of this domain, what are the endpoints of the domain? On the left side, the minimum possible point, you could say, is 0. Although 0 is not included, but greater than 0 would basically mean 0.000000000, and then infinitely many zeros, and maybe a 1, right? So you can say one endpoint is 0, all right? So that's the least possible value, as in one extreme value, 0. Although 0 itself is not included, but it should be something very close to 0, okay? So that's one extreme point, one end point on the lower side. What about the endpoint on the other side? It's x greater than 0. Is there any maximum possible value of the domain? On the maximum side, on the upper side, the maximum possible value, we can say that's infinity, right? So it's going towards infinity on the right side. That's what we have on the right side. So the values of x, they could go from 0 to infinity. All right. Now we need to see, if these are the values of x, what about the corresponding values of y? What about the corresponding values of y? Let's see what happens when x is 0. Let's just input that here. F of 0, right? Let's see what the function's value at that point is. 3 over 2 into x plus 1. That means 0 plus 1. What do you get from this? 3. So when value of x is equal to 3, x is equal to 0, the value of the function, the y value is 3. So for y, we've got one endpoint. We're saying y is supposed to be between 3 and some other value. Let's see what we get from the other point. So we get y equal to 3 when x equals 0. What happens when x is infinity? Any idea about that? So if we were to input x equal to infinity, what would happen to this function? Any idea?
Sir, 0.
It'll become 0, right? When
Yes.
you have infinity in the denominator, that means the denominator becomes extremely large, right? The denominator becomes extremely large. If the denominator is extremely large, 3 over that extremely large number is going to be 0. Okay, so you can kind of think of it like this: 3 over 2 times infinity plus 1, right? 2 into infinity plus 1 is also infinity. 3 over infinity, 3 over an extremely large number, that's going to be 0. All right. So in the denominator, since you have an extremely large number, you can say that fraction is going to approach 0. Make sense? Now, if you can't figure this out in your head like that, another possibility is you just put this on your calculator like this. So infinity means an extremely large number. So just put an extremely large number on your calculator. So maybe f of 10 raised to power 10, right? And see what happens with that value of x. If you try putting that on your calculator is going to give you something like this: 2 into 10 raised to power 10 plus 1. Try putting this on your calculator. You will get something like this: 0.000 and so on. So an extremely small value. And that basically tells you that this is approaching 0. This is approximately equal to 0. So what's the range then? What's the range of this function then? We would say the range of the function is y between 0 and 3. Okay, y is between 0 and 3. Now we are not going to have equal to sign with either of them in this case. Why? Because when you input x equal to 0, you get 3. X equals 0 was not included, right? There was no equal to sign with x equal to 0. That means the corresponding value 3, we will not have an equal to sign with that. So that's decided. With 3, we are not going to have the equal to sign. What about 0? When denominator becomes extremely large, this value is going to approach 0. It's not going to be exactly 0 because in the numerator we still have something. We have 3 over something. So that number is going to be it's still going to be something. It's not going to be exactly 0. It's going to be extremely small. So we're going to say it's almost equal to 0. Now, since it's almost equal to 0, it's not exactly 0. We can't put an equal to sign with 0 here because it's not exactly equal to 0. It's approaching 0. So that's the range of this function. The range of the function would be y between 0 and 3. That's how we would find this range. Does this make sense?
Yes, sir.
Okay. Let's take another example. Let's say we have another function that looks like this. We have g of x. Again, it's taken from a past paper. 1 over x plus 2. And you're given that x is greater than 0. How do you find the range of this function now? Again, think of the endpoints of the domain. Again, it's x greater than 0. That means the endpoints of the domain are from 0 to infinity. All right? 0 to infinity. Now, what about the corresponding y values? Let's figure that out. We have 0 here. We could try inputting 0 and see what that gives us. G of 0, that equals 1 over 0 plus 2. Well, we have a problem here. We have 1 over 0 that's undefined. So we can't really input 0 in this function as such. 0 cannot be input here, right? In the previous case, when we input 0, we did not get 0 in the denominator. We had 1 in the denominator. So we could evaluate the result. Now, in this case, we can't really input 0 like this because that's becoming undefined. So what do we do instead? Since it's greater than 0, we tried inputting 0, that did not work because that gives you 0 in the denominator. What you can instead do is, since it's greater than 0, you can input a value slightly greater than 0, just slightly greater than 0, and see what happens when that is the case. So try inputting, for instance, x equal to 0.000001, something like this, right? An extremely small value. Or maybe, let's try to this, write something like this, 10 raised to power minus 10. Right? That means it's an extremely small value. Okay, 10 is 10 to minus 10, that's an extremely small value. Try inputting that and see what happens. 1 over 10 raised to power minus 10 plus 2. Put that on your calculator and see what happens. What do you get? You get an extremely large value, right? It'll be 1 and then many zeros like this, and then maybe a 2 at the end. It's an extremely large value.
Sir, it's 1 into 10 raised to power 10.
1 into 10 raised to power 10, but you have also have plus 2 with that, no? So that's going to be, there's going to be a 2 at the end somewhere. Right, so it's 10 raised to power 10 plus 2. So let's write it like that, 10 raised to power 10 plus 2. And that's an extremely large value. So what we need to understand is it's an extremely large value. Now, if this value was even smaller, as in it's greater than 0, right? That means we could have a value that's extremely small on the positive side, 0.000000, and let's say infinitely many zeros, and then maybe a 1. So 1 over an extremely small value, what is that going to give you? This is going to give you infinity. Infinity plus 2. So basically, when x is equal to 0, the result that you get is infinity. When x is something very close to 0, the result that you get is infinity. Does that make sense? When the value of x gets close to 0, the value of the function goes towards infinity because this number is going to be extremely large. This number, 1 over small value, that's something very large. That's going to go towards infinity. So close to 0, this function basically goes towards infinity. Does this make sense to everyone? All right. Now, what about this? When x is going towards infinity, what happens in that case? In this case, you can try and putting a very large value. You can think of it logically as well. It's not necessary to show all of this working. You can do this in your head as well, that, okay, if x becomes very small, that means this whole function is going to be very large. So one endpoint that you get is infinity. And if x becomes extremely large, if it goes towards infinity, what happens in that case? This is going to become 0. And you're just going to be left with this 2. You can try that. Try inputting this on a calculator. Try inputting a large number. Again, 10 raised to power 10, you can try that. What does that give you? 1 over 10 raised to power 10 plus 2. Now, this is an extremely small value. So this is going to be close to 0. Then you have plus 2 with that. And this is going to approach 2. So on one end, the function is going towards infinity. On the other end, the function is going towards 2. So what should be the range of this function? We would say the range of this function, therefore, is y between 2 and infinity. Or we could write it like this. We could say y greater than 2, right? So infinity is not really a number as such. We could just write it like this, y greater than 2. Both of them are going to be okay. This is also fine. This is also fine. Both of them are acceptable. We can say y is between 2 and infinity, or in other words, we could say y is greater than 2. Does that make sense?
Yes, sir.
No questions? Okay, so basically, if you have linear functions or quadratic functions, since you know how to sketch the graphs for them, it's easier to think of them by sketching a rough graph. That's going to save you from careless errors. Similarly, for quadratic functions as well, you know how to sketch the graph of that function. You could do that to help with your calculation. In this case, it's a reciprocal function. You will find it hard to draw the graph. That's going to require quite some thinking. So here we could do it without the graph. Since we know we are not going to have any turning points, we just look at what happens at the end point, right? What happens when x is at its minimum value and what happens when x is at its maximum value. We just see what happens at those two extreme points of x, extreme values of x, and that's going to give us the range of the function. Okay, let's take another example, and then we'll move on to the next concept after that. I'll give you a minute to think about this. Let's say you have f of x equal to 1 over x minus 2 whole squared, and the domain of this function, let's say, is x greater than or equal to 5. Again, we're looking for the range of the function. Okay, take a minute, think about the range of this function, use the same logic that we used before. Let me know what the range of this function should be. Yes, can I have responses in the chat box? What do you think the range is? Okay, so I have a couple of responses. Both of them look almost correct, as in the idea is correct, but yeah, so one of them is completely correct and the other is maybe in the reverse order. So that's good to see. What about the others? Can everyone respond? Hira, Naima, Rajal, Aram, what's the range of this function? Send messages to the account that says message here. Send your answers to that account. Abdullah, what's the smaller number, 0 or 1 over 9? The smaller
0,
number
sir.
is the smaller number should be on the left side, and the larger number should be on the right side. Okay, but that's good. Okay, so how do we start? We think of the endpoints of the domain. What are the endpoints of the domain? 5 and infinity, right? These are the endpoints of the domain. Now, what happens when x is 5 and what happens when x is infinity? Can we input 5 in the function? Yes, we can do that. We don't have a problem here. In this case, inputting 5 does give a result. So 1 over 5 minus 2 whole squared. What does that give us? That gives us 1 over 9. All right. Yes, Rajal, that's correct. Although we should write it the other way around. I'll just show that to you. F of 5 equals 1 over 9. So that's one extreme point that we're getting. Okay. What happens when x goes towards infinity? Again, we can think of what would happen to this fraction when x goes towards infinity. The denominator becomes very large. When the denominator becomes very large, the whole fraction goes towards 0. Okay. We can try inputting a large number. We can say 10 raised to power 10. Let's input that here. That equals 1 over 10 raised to power 10 minus 2 whole squared. Put this on your calculator. Your calculator is going to give you an extremely small value. So you would say this is almost equal to 0. So what's the range of the function then? The range of the function is y between 0 and 1 over 9. Now, 0 is not included because the value is not exactly equal to 0. So 0 is not going to have an equal to sign with it. However, 5 was included. That means the corresponding value of 5, which is 1 over 9, that should have an equal to sign here. So the range is from 0 to 1 over 9 with 1 over 9 included. That would be the range of this function. Okay. Now, this is the standard way of writing it. This would also be logically correct. 1 over 9 greater than y greater than 0 like this. That makes sense mathematically. That's correct. But generally, it's a convention to write such inequalities in this form, such that the smaller number is what you have on the left side, the larger number is on the right side, and we have less than signs. This also is correct mathematically, but conventionally, what we do is we write smaller number on the left side, larger on the right side with less than signs. So that's what is generally given in the marking scheme. So I would recommend that you do this in case they deduct marks for this for some reason. Okay. Because this is the convention. Smaller number on the left, larger number on the right. Okay. That's the range of the function. So now we know how to find range of linear functions, how to find range of quadratic functions, and also how to find range of rational or reciprocal functions. Now, you could actually use the same method for linear functions as well, because linear functions also do not have any turning points. So in this case, for instance, x greater than or equal to 3, you could think of what happens when x is 3 and what happens when x is infinity. When x is 3, you get 19. When x goes to infinity, y is also infinity. So that gives you this range. You could do linear functions using that same idea without drawing graph as well, right? Because linear functions don't have any turning points. In this case as well, you could get away with not drawing graphs and just using that same logic that we used for reciprocal functions. For example, if you had this, x is from 5 to infinity, you could try inputting 5. 5 gives you y as minus 5, and infinity gives you, if you input infinity here, a very large number x, the y value is going to be very large negative value. That's negative infinity. So range would be between negative infinity and negative 5. You could say that's y less than minus 5. So that could be one way of doing these linear functions as well, if we don't want to draw graphs there. However, for quadratic functions, you always should be drawing graphs. You should always be sketching graphs, because here we have turning points, and turning points cause some confusion. So after sketching the graph, you're just going to see, okay, what's the highest point on the graph and what's the lowest point on the graph? Vertically, what's the lowest point, what's the highest point in the part that is defined, okay? In the part of the graph that is part of this domain. So for quadratic functions, always sketch graphs. For linear functions, you could try doing that mentally as well. That will work, although I think it's still safer to sketch the graph. That will save you from careless errors. All right, so that's how we find range of different kinds of functions. Now, these are three specific types of functions that come quite frequently. You could get other types of functions as well. You would just use the same logic. What's the logic? Look at two types of points, endpoints and turning points. So for any function to find the range, you would look at what is happening at the endpoints of the domain and what is happening at the turning points. And then using those, you just write the range. Whatever is the highest value, that's the maximum point of y, that's the maximum possible value of y. And whatever is this lowest value on the graph, that will be the least value of y. Okay, so you will see other types of functions when you do some problems as well. The logic is going to be the same, but these are three types that come very frequently: reciprocal functions, linear functions, and quadratic functions. Let's move on. And now we need to discuss inverse functions. Now, we talked about inverse functions before as well, but in O levels, you have only learned how to find inverse of linear functions. Now, here we will be learning how to find inverse of some other types of functions as well. Okay, so if it's not a linear function, for example, if it's a quadratic function, if it's some other function, maybe a trigonometric function, how do you find inverse of functions like that? That is what we want to learn next. Now, for that, you first need to know something that we call types of relations. Not relationships, types of relations. So mathematical relations. Okay, types of mathematical relations. There are basically four different categories that we divide mathematical relations in, and they look like this. So we have one-to-one relations. Then we have many-to-one relations. One-to-many relations. And then number four, you have many-to-many relations. You have these four types of relations: one-to-one, many-to-one, one-to-many, and many-to-many. Okay, these are four types of relations that you will be dealing with. Now, what does this mean? The first word that you see here, that basically refers to the input of the function. The first word refers to input of the function, and the second one refers to the output of the function. Okay, so these are four different types of relations. One-to-one relation basically means you have one input and one output. For every single input, you get one possible output. Okay, that's what one-to-one relation means. Now, let me explain that using an example. So first of all, let's start with these one-to-one relations. One-to-one relations. Now, one-to-one relations basically look like this. For instance, you could have a straight line, for instance. That's one possible one-to-one relation. You have y here and you have x here, and maybe you have a line like this. Now it's a straight line. What's special about this line is, and about every line is, not every line, but most lines is, that for every single value of x, you have only one value of y. For example, if you have this value of x,
Sir, sir, we cannot hear you.
okay, I'm sorry, I got disconnected. Let me repeat what I said. So basically, we're saying for every single value of x on this graph, we have only one value of y. For example, for x1, corresponding to x1, we have only y1. Corresponding to x2, we have only y2. For every single value of x, we have only one value of y. And it's also true the other way around. For every single value of y, for example, this value of y, we have only one value of it. That's what one-to-one relations are. That for every value of x, we have one value of y, and for every value of y, we have one value of x. One x for one y, one y for one x. Okay, that's what a one-to-one relation is. Now, you could have straight lines for that, like this. You have other functions like that as well, not just straight lines. You will see later on in paper 3, for instance, you would have functions like this as well. You have a log function, for instance, or an exponential function. Exponential function, for instance, looks like this. One possible shape of exponential function that looks like this, right? Now, this function is also one-to-one. Why? Because for every single value of x that you can input here, let's say this value of x, you have only one value of y. And for every single value of y here, you have only one value of x. Okay? You could have exponential function, you could have log functions as well. And if you think about it, these reciprocal functions, these are also one-to-one functions, the ones that we've done. Here as well, for every value of x, you have only one value of y. For every value of x, you have only one value of y. For every value of y, you've got only one value of x. So it's one-to-one both ways. All right. This is what one-to-one functions are. That for every one value of x, you have one value of y, and for every one value of y, you have one value of x. Now, there's something that's interesting about these one-to-one functions, and that is one-to-one functions do not have one-to-one relations, or as we will call them later, we will call them functions as well. One-to-one functions do not have any turning points. They don't have any turning points, because if you have a turning point, then the function would not be a one-to-one function anymore. If there's a turning point in the middle of the graph somewhere, if it looks like this, for instance, then this is not a one-to-one function. We'll see in the next example now. So this is a one-to-one relation. The next type of relation that you have is many-to-one relation. And you will see in many-to-one relations, you will have turning points. Let's take an example of a many-to-one relation now. One-to-one relations, by the way, this is one example. Let me actually write down some examples of this as well. For example, we said we could have linear functions here, right? These are one-to-one. You could have exponential function e power something. You'll see this later in paper 3. You could have log function. Again, you'll see this later in paper 3. You can have functions like these, right? So for now, you can just note it down. When you do paper 3 later next year, you could look back at it and see that, okay, exponential function is also one-to-one. ln x is also one-to-one. You will need to use these concepts in paper 3 as well. So these are some examples of one-to-one functions. Now, what about many-to-one? Many-to-one basically means, remember, the first word refers to input, right? So input means values of x, output means values of y. So the first word refers to input. So if you have many x and one y, what does that mean? What type of function it could look like? You could have a function like this, for instance. If you have x and y axes looking like this is y axis, this is x axis. If you have a function like this, for instance, which function has a graph like this? Quadratic function, right? Quadratic functions graphs look like this, right? Now, this is not a one-to-one relation. This is a many-to-one relation. Why? Because we can have multiple values of x that can give us the same value of y. For instance, if I have this x here, let's call this x1, and I have this x here, let's call this x2. At both of these x values, the y value is the same. We're getting the same y value at two different x values. That means many x, yani multiple x, are giving us single y, one y, right? Many x are giving us multiple y. Sorry, many x are giving us one y, single y. So that's many-to-one relation. Multiple values of x are giving us single value of y. Okay, that's a many-to-one relation. Now, these have turning points, right? So many-to-one relations have turning points. Many-to-one do have turning points. Okay, so that's one way to look at whether the function is many-to-one or not. It has a turning point. Okay. Now, what are some examples of these functions? What are some examples of these relations? One is quadratic, right? We have seen this here. You could have quadratic functions, for instance. You could have any other polynomial, like cubic functions. Not all cubic functions. Some cubic functions are one-to-one. Some are, most are many-to-one. So you could have cubic, quartic, always. Trigonometric functions, sine, cos, right? Remember their graph? Sine graph looks like this. Cos graph looks like this. They are also many-to-one functions because they have turning points, right? Multiple x values can give you one value of y. So this is a many-to-one relation as well. All right. Then you have two other types of relations. which are one to many and many to many. Let's look at that. Look at those quickly as well. One to many. Let's start with this first of all. One to many basically looks something like this. You could have a graph like this, and let's say you have this. This is a one to many relation. This is a one to many relation. Now, what does one to many mean? One to many means you could have one value of x that's giving you many values of y. Now, for instance, I could take a value of x here. Let's say this value of x, right? Let's call this x. Now, at this x, I'm getting two y values. I'm getting one y value above there and another y value here. There are two different y values that I'm getting for one value of x. So one input is giving me multiple outputs. This is one to many, right? One input is giving us multiple outputs. Now, one example of a relation like this is this: y squared equals x, something like this. Now, not exactly this, but there will be some constant added or subtracted here, maybe. If you were to rearrange this, it would look like this: y equals plus minus square root of x. So one example of such functions, if you write that here, is square root function. Square root relation. And it could look like this: y equals plus minus under root x. If you have something like this, the graph of that function would look similar to this. Not exactly this, as in it might be towards the left a bit, towards the right a bit, or maybe up or down somewhere. But this is the type of function for which you have a graph like this. This is a one to many relation. That means for one value of x, you're getting multiple values of y. Now, it's not necessary for you to remember this, that what type of function you have, what type of relation gives you a graph like this. But just remember, if you have a graph that looks like this, that's a one to many relation. Okay. And then we have the last type of relation that's called a many to many relation. And that basically is that one value of x can give you multiple values of y, and also the other way around. One value of y could come from multiple values of x. Now, let me show you an example of this. You could have a graph that looks like this. Now, we will do this later on when we do equation of circle. We haven't done that yet. But if you had a graph of a circle like this, or maybe an oval as well, right? Oval as well. This is also many to many. But let's say we have a circle. You will be doing this later on. Equations of circle. Now, in a circle, you could say you have multiple values of x that can give you one single output. So for instance, I could take one value of x here. This x can give me one y here. Let's call this y1. And it could give me another y here. There are two values of y that I get as a result of x here. And similarly, one value of y could also give me multiple values of x. For example, if I consider this y, I get two possible values of x corresponding to that. One is here and the other is here. So we have x1 here, x2 here. So one value of x can give you multiple values of y, and one value of y could come from multiple values of x. Okay, that's the idea. This is a many to many relation. It's a circle. You could have an oval as well. These are some graphs that are many to many relations. Okay. Now let's summarize that. So we have four types of relations then. Let me write them down here again. I could just copy that. Let's begin. In fact. So number one, we have one to one one-to-one relations. Then we have many-to-one relations. Then we have one-to-many relations. And then finally, you have many-to-many relations. These are the 4 different types of relations that we have talked about. Okay. And we know the first word refers to the input as an X. And the second refers to the output, which is Y. Okay. Now I'm actually write it a bit more clearly here. All of this is the input, and this is the output. These are 4 different types of relations. Now, there's something that we call a mathematical function. All of these are relations, one-to-one, many-to-one, one-to-many, and many-to-many. These are 4 different types of relations that we have. But not all of these are called functions. The condition that we have for a mathematical function is that a function can only give you one output. A function in mathematics is defined as something that can only have a single output. You can't have multiple outputs. Okay. So you might have, so those of you doing computer science as well, you do have functions in computer science that give you multiple outputs, right? So you can have a function defined like that gives you multiple outputs. But in maths, by convention, what we do is we call only such relations functions that have a single output, one output. Okay, that's just by definition. A mathematical function is a relation that has a single output. What that means is one-to-one relations are functions, many-to-one relations are functions, but one-to-many and many-to-many, these are not functions. So we will only be dealing with these first 2 types here, not the 3rd and 4th types, right? Because we're doing the functions topic right now. Okay. Since one-to-one and many-to-one are the only relations that are functions, we will only stick to those 2 types. Okay. And then, since we are now going to talk about inverse of functions, inverse only exists when a function is one-to-one. Let me write that here as well. How do you know if inverse exists or not? Inverse of a function only exists if it is one-to-one. So for a one-to-one function, the inverse exists. For a many-to-one function, the inverse does not exist, right? Since we're not even talking about the other 2, so we will skip them. We're just talking about the first 2 types here. One-to-one and many-to-one. So a relation is only a function when the output is only one, when there's only one output, right? Only then you have a function. And then out of those 2 types of functions, one-to-one and many-to-one, only one-to-one functions have inverse. Many-to-one functions do not have an inverse. Okay? Only one-to-one functions have inverse. Okay? Let me write that down. Inverse only exists for one-to-one functions. All right, inverse only exists for one-to-one functions. Now that's what we need to understand about relations. And we said inverse only exists for one-to-one functions. Okay. Now, this is one thing that we want to discuss here in addition to this, and that is, how can we figure out, looking at the graph of a function, a function, whether this function is one-to-one or many-to-one? So there's basically a test that you need to know about that we will be using sometimes in some problems, and that's called a horizontal line test. So sometimes you will have a function given, and you would have to figure out whether that function is a one-to-one function or a many-to-one function. Now let's see how we can figure that out looking at the graph of that function. Now, what's a one-to-one function and what's a many-to-one function? What's the difference between the two? A one-to-one function is when every value of x gives you only one value of y, and every value of y gives you only one value of x. This is a one-to-one function. In a many-to-one function, you can have multiple values of x that give you a single value of y. That's a many-to-one relation or many-to-one function. How do you differentiate between the two? If we have the graph of the function given, there's a test that we call a horizontal line test. And that works like this. If I were to draw, you can basically ask yourself a question. Can you draw any horizontal line on this graph that would cut the graph at 2 points? So if you have a straight line like this, can you draw any line on this graph, any horizontal line on this graph that would cut the graph at 2 points? You can try that. You could have a line like this. It only cuts at 1 point, 1 point, 1 point, 1 point. Whatever horizontal line you draw, it only cuts the graph at a single point. All right. In this case as well, you can try drawing horizontal lines. All of them cut the graph at only one single point. They do not cut at multiple points. If there's no horizontal line that you can draw that cuts the graph at more than 1 point, that's a one-to-one function. In this graph, think about it. Can you draw any horizontal line that cuts the graph at 2 points? Well, yes, you can. You can draw this line. If you can draw any one horizontal line, at least one horizontal line, that cuts the graph at 2 points or more than 1 point, it could be 2, 3, 4, that means it's not a one-to-one function. Why? Because if the horizontal line is cutting the graph at 2 points, that means this point and this point have the same y value, and these are two different x values. So two different x values are giving you one single y value. That means it's not a one-to-one function. So that's what a horizontal line test is. So basically, you ask yourself this question. I'm going to write that down here now. Horizontal line test. You basically ask yourself this question. Can you draw at least one horizontal line on the graph that cuts it at more than 1 point? You basically ask yourself this question. Can you draw any horizontal line that cuts the graph at more than 1 point? If the answer to that is yes, that means it's not a one-to-one function. Right? Because if it's cutting at multiple points, it's not a one-to-one function. If you cannot draw any such line, if the answer to that question is no, then you say it is a one-to-one function. Okay. So if you can draw at least one horizontal line that cuts the graph at more than 1 point, that means it's not a one-to-one function. If you can't draw any line, that means it is a one-to-one function. So here, in this case, you can draw a horizontal line that cuts the graph at 2 points. That means it's not one-to-one. Now, not every single line has to cut at 2 points. For example, if I were to draw a line here that does not cut the graph at all, but can I draw at least one such line? yes, I can draw this line at least. So even if it exists for one single line, we say it's not one-to-one. In the previous case, in this straight line or in this curve, you can't draw any line, any horizontal line that would cut this graph at 2 points. In this case, it's not possible. So that's why it's a one-to-one function. All right, so that's how we can differentiate between a one-to-one function and a many-to-one function. All right, make sense? Now let's talk about inverse. All of that discussion was basically to get to this point. Number one, a function is one that has one single output. So many-to-one function or one-to-one function. Inverse only exists for one-to-one functions. All right. So now we need to understand how to find inverse of different types of functions. So first of all, we could talk about inverse of linear functions. Now we've already discussed this before. I'm just going to copy that here. We looked at this earlier. How to find inverse of linear functions, right? We did this in our very first class, this whole process. This is how this process works. If you have f of x equals 2x plus 5, we said we're going to replace f of x with y. All right. In fact, you could use this shorter working, this one. All you have to do is this. Replace f of x with y. That gives you y equals 2x plus 5. And then you make x the subject, and you get this. Replace x with f inverse, replace y with x. We'll discuss the logic of that as well. How when you do y equals f of x, it becomes x equals f inverse of y, and then you replace x with f inverse of y at the end here, and then you replace y with x. That gives you this inverse function, but you could just skip some of those steps to write the inverse down like this. So you just have to do these 3 steps. We actually wrote those steps here as well. This is all that you have to do for linear functions. Let y equals f of x. Make x the subject. Replace x with f inverse of x and y with x. That's all that you've got to do, and that will give you the inverse of the function, right? So for linear functions, it's a very simple process like this. This is how we can find inverse of linear functions. Now there's some properties of a function and its inverse that we need to know about. We'll quickly discuss them, and then we end for today. In the next class, we will discuss how to find inverse of quadratic functions. Even though quadratic functions are not one-to-one, we will first make them one-to-one and then find the inverse of those functions. But that's for the next class. For now, let's look at a couple of properties of inverse functions before we end. So in this case, we have seen this example before in our very first lesson on functions. That was actually yesterday. We found that if you have a function f of x, which is 2x plus 5, its inverse turns out to be x minus 5 divided by 2, right? So if you have this function, the inverse is this. Now, why do we call these functions inverse of each other? Why is the second function inverse of the first? Because if you were to input, for instance, x equal to some value in the first function, for example, 0, what value of y do you get from this? You get y equal to 5. If you were to input x equals minus 2, for instance, what value of y do you get? Y equals 1. If you input x equals 3 here, for instance, you get y equals 11. Inputting x equals 0 gives you y equals 5, minus 2 gives you 1, 3 gives you 11. In the inverse function, if you were to now input these values, try x equals 5, try x equals 1, try x equals 11, what would happen would be you would get those original values back. So if you input 5, you get 5 minus 5, that's 0, 0 over 2. y equals 0. When you input x equals 1, you get minus 4 over 2, which is minus 2. When you input x equals 11, you get 11 minus 5, that's 6 over 2, y equals 3. So you see what's happening? X and y are interchanged here, right? Earlier, x equals 0 was giving you y equals 5. Now x equals 5 is giving you y equals 0. That's what an inverse function is supposed to do. It interchanges x and y. Okay, x becomes y and y becomes x. All right. Now, that gives us something very important that you need to know for inverse functions, and that is, if you have a function f of x, and you have the inverse of that function, f inverse of x, these two functions are going to be related to each other like this. The domain of the original function, the domain of f of x, that is going to be the same as the range of f inverse of x. Why? Because domain represents values of x, range represents values of y. So x of the original function becomes y of the inverse function. So we can say domain of the original function becomes the range of the inverse function. Okay. So for instance, just as an example, let's say the domain of this function was x greater than 0. Let's assume x greater than 0. The range of the inverse function would be y greater than 0. Okay, you can't write x greater than 0. It's going to be greater than 0, but since it's range, we will say y greater than 0. And similarly, the range of the original function, that is going to become the domain of the inverse function. They're going to get interchanged. Domain of f of x is the range of f inverse. Range of f of x is the domain of f inverse of x. Okay. Now, what would be the range of this function? Think about this. At x equals 0, we get y equals 5. It's an upward sloping graph like this, right? So we have some point here when, if the domain is x greater than 0, let's say. So we have one point here at which x is 0 and y is 5. Which part of this function is relevant, is valid? This right part. So what's the range of the function then? Y greater than 5, right? So if x greater than 0 is the domain, then the range would be y greater than 5. So range of the original function is y greater than 5. What does that mean? What about the range? Or what about the domain of the inverse function? The domain of the inverse function would be x greater than 5. Okay, so domain of the original function becomes the range of the inverse function, and range of the original function becomes the domain of the inverse function. Okay. Now, one last thing before we end, or maybe we can do this in the next class then when we talk, or should we do it right now? Well, let's actually connect all of this. Otherwise, it will be, I'll have to revise all of this for the next class. So I'll quickly do that. So let's say you have to sketch a graph now. So you sometimes need to sketch graphs of functions as well. So let's say you have a function like this, f of x that equals 4x minus 2. You need to sketch the graph, sketch f of x and f inverse of x on the same diagram. Showing the relationship between the two graphs. Showing the relationship between the two graphs. Okay, so you want to sketch f of x and f inverse of x in the same diagram, showing the relationship between the two graphs. And this is what f of x is. Now, how do you do that? you will draw X and Y axis like this, right? So let's say this is X axis and Y axis. How do you draw the graph of this function? 4x minus 2, that's a linear function, right? You just have to take some value of X and some value of Y, plot them, and just join them. It's a straight line, so you just need two values, right? You can try X equals 0. When X equals 0, what's the value of Y? The Y value is minus 2. So that's going to be, let's say here, this is negative 2. So the graph is going to pass through this point. And then take another value, let's say when you have X equals 1, the value of Y is 2, right? When X equals 1, the value of Y is 2. So let's say this is 2 here. And on the horizontal axis, now this is very important. When you draw this graph, on both the axes, you should have the same scale. Let me write that here. We call this using a square grid. That means use the same scale on both axes. Now I'll explain why that it's important in a few minutes. Use the same scale on both axes. That means whatever you have represented as 1 unit on the horizontal axis, the same distance should be represented as 1 unit on the vertical axis. So use the same scale on both axes. And that is important because we need to show something graphically here. A relationship between the two graphs. Otherwise, it will not be very clear. So roughly on both axes, it should be the same distance that you're calling 1 unit. So we have one point here that's 0 and minus 2. You could try another point, try inputting, for instance, X equal to 1 here. So when you have X equals 0, Y is negative 2. If you have X equals 1, Y is 2. Let me mark another point here. That's another point. I could draw a graph using these 2 points. It's a straight line. So these 2 points are going to be enough. The graph is going to look something like this. This is the graph of Y equals, or f of X equals 4x minus 2. Now, what about the graph of f inverse of X? Now, we could find the function f inverse of X here if we wanted, and then plot values in that function, input values in that function, take a couple of points and then draw that. That is one possibility. However, since we know in an inverse function, what happens is the values of X and Y basically get interchanged. So this point is 0 and minus 2 on the original function. This point is 1 and 2 on the original function. When you draw the graph of the inverse function, what happens is these coordinates just get interchanged. So in the original function, if you had something like this, x, y, in the inverse function, what that becomes is yx, right? That's how you find inverse in the first place. You interchange x and y, right? So x, y becomes yx. And that can help you draw this graph now without actually finding the inverse function. So if you just had to sketch this graph, you would say, okay, 1 point on the original function is 0, minus 2. What about the inverse function? The inverse function would have minus 2, 0. So you have, let's say, minus 1 here and minus 2 here. So 1 point that you have on that inverse graph, therefore, is this one. This is minus 2, 0. And similarly, you could reverse this point as well. It's 1, 2, interchange these coordinates. It becomes 2, 1, and that's this point. This is going to be a point that lies on the inverse function. And now you can draw the graph of the inverse function like this as well. It's going to look like this. Without actually finding the function, you can draw the graph like this. This is the graph of f inverse of x. Okay? This is how the graph of f of x and f inverse of x looks like. Now, if you remember your O-level transformations, we will actually need them in this topic as well when we do function transformations. Remember when this used to happen? When did xy used to become yx when you did transformations? when did the coordinates used to interchange like this? This used to happen when there was a reflection in the line y equals x. So if we look at these two graphs are actually reflections of each other in this line y equals x. So if I were to draw this line here, y equals x, these two graphs are reflection of each other in this line. So whenever you draw the graph of a function and its inverse, what you would always do would be, you would draw this y equals x line as well to show that f of x and f inverse of x are a reflection of each other in this line. So what do you say here? Y equals x, you've drawn that line. And now, since it said showing the relationship between the two graphs, so what's the relationship between the two graphs? The relationship between these two graphs is that f of x and f inverse of x, they are reflection of each other. They're a reflection of each other in the line y equals x. All right. F of x and f inverse of x, they're a reflection of each other in the line y equals x. And that is always the case. It's not just specific to this particular function. It's true in general. Whenever you have a function and its inverse, they are related like this. F of x and f inverse of x, they are going to be reflections of each other. Okay. So that's a general rule that works here. So how do you draw graphs of f of x and f inverse of x? What you can always do is, without actually finding the function, you could just interchange their coordinates and just join those 2 points, join those points like this. 0 minus 2 becomes minus 2, 0. And 1, 2 becomes 2, 1. All right. And then you can draw the graph like this. Now, why is it important to use the same scale on both axes whenever you draw graphs of functions? Because otherwise it would not be very clear. The reflection would not be very clear in that case. In this case, since we have the same scale on both axes, we can see that the graphs are a reflection to each other. It's visible on the graph that they are reflections of each other. However, if the scale was not the same, let's see what it would look like if it was not the same. If you were to distort it such that the scale on the horizontal axis was bigger, so now we have more distance between values on the x-axis as compared to values on the y-axis. You see, the graph is distorted. Now, f of x and f inverse of x, they don't look like reflections anymore. The perpendicular distance here is no longer equal, right? So they're not reflections, and they do not look reflections anymore. If you had the same scale like we had originally, the scale is same. Here they look like reflections of each other. Perpendicular distance from the line of reflection, they are equal on both sides. So that's why it's important to always use the same scale. Sorry about that. Always use the same scale whenever you're drawing the graph of f of x and f inverse of x. Does that make sense to everyone?
Yes, sir.
Okay. So now we understand, we've done 3 things today. How to find range of reciprocal functions, right? We started with that. Then we discussed the different types of relations. 1-to-1, many-to-1, 1-to-many, many-to-many. Only the first 2 are functions, and the inverse only exists for 1-to-1 functions. Then we talked about this horizontal line test to figure out whether a function is 1-to-1 or not. And then we already knew how to find inverse of linear functions. We knew the process for that. But then we need to understand this relationship between a function and its inverse, that whenever you have a function at the and its inverse, the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function because x and y get interchanged. And then we talked about the graph. The graphs of f of x and f inverse of x, they're always reflections of each other in the line y equals x. Whenever they ask about this, you will always draw this line on the graph y equals x whenever you're drawing graphs of f of x and f inverse of x, and you would write that they're reflections in this graph. Okay, any quick questions before we end? Any problems, anyone?
No, sir.
No? All right, so we will continue this from here. You are not going to be able to do a lot of questions from the worksheet yet. We have covered quite a few concepts, but the thing is, the questions on functions, they generally have domain and range problems in one part, and then in another part, they ask you about something else. After the next class, you should be able to do most of the questions from the worksheet because a lot of questions are on quadratics. So in the next class, we will learn how to find inverse of quadratic functions. And then after that, you should be able to do a number of questions from the worksheet. I'll be uploading the worksheet today anyway. You can have a look at those questions. We'll be starting to do some of those practice questions in the next class, inshallah. All right, that's it for today. I'll see you again in the next class. Allah Hafiz.